Hello everyone, we're presenting today our work, Reconfigurable Robot Control using Flexible Coupling Mechanisms. Army ants are especially known for their capability to traverse challenging terrains, for example, a dynamic gap. Robots can also encounter similar terrains when performing search and rescue or exploration tasks. In our previous work, we have 4 robots starting from unaligned positions. They form a rigid assembly and go across a gap and decouple to continue their tasks. However, rigid structures have limited motion after coupling and require a perfectly flat surface to operate. Additionally, they can only handle limited height difference. In this work, we present a soft and compliant connection that provides more flexibility while maintaining a strong and reliable connection. Our mechanism consists of an asymmetric soft anchor that has 2 degrees of freedom. It can extend along the x-axis and rotate around the z-axis. The asymmetry in the anchor allows one robot to easily connect with another robot, while the force required to decouple is significantly larger than the coupling force. When the anchor is inserted, the tips sit inside the slits of the opening on the other robot. When one robot drops with gravity, the anchor locks and provides a strong holding force. We can also control the rigidity of the assembly. Robot can still form the rigid connection as in previous work by coupling on the side. They can also form a flexible chain that is compliant to environment structure. Modeling soft connections can be difficult. We simplified our design so that it can be modeled as a 3-bar linkage in simulation. The parameters in the simulation is obtained from the force profile of the actual anchor. Here we show 2 robots coupling with each other. Robots can decouple with the wiggling motion. Modeling soft connections is challenging. Previously, with the rigid connections, we modeled the coupling constraints by maintaining connection points within a small distance. However, this is very restrictive to the robot motions. The QP-based optimization also gives very suboptimal results. Modeling soft anchor connection can be even more difficult since we do not have direct access to the coupling status. Incorporating the full dynamic constraints of the anchor is also computationally heavy for non-holonomic systems. Therefore, we modeled our coupling constraint as a linear pointing polygon constraint. We can then formulate an MPC framework for controlling an assembled structure. The cost of our MPC framework consists of the terminal and stage cost for target connection pairs, stage cost for already connected pairs, and the smoothness cost. Then we have the initial state constraints, dynamic constraints for the unicycle model, the pointing polygon constraint we just mentioned, and the actuation limit on the wheels. Here we show 4 robots in simulation coupling in a line. Our couple assembly can also move on rough surfaces. We can generate a random rough surface and 3D print it. 2 robots can traverse as assembly on this rough terrain. The structure can also rotate as assembly, which was not possible for rigid structures. Robots can also connect and go down a stair. Thank you. All our code is open source in the link below.